Hi, I'm Andrew Choi. Welcome. This is my presentation for Complex 529 Assignment 3, Paper 3. The paper to be introduced is Automatic Application Placement and Adaptation in Cloud Edge Environment, written by Sebastian, Meixner, Daniel Schall, Vasileios, Karagiannis, Stefan, Schulte, Konstantinos, Plakidas. The paper was published in 24th IEEE Conference on Emerging Technologies and Factory Automation at Spain in 2019. The author noticed the deployment of automatic application is becoming more complex from local cloud to the edge computing from the microservices perspective, which will be the new challenge to the operational staff to design the place to optimize the application performance. Yet the decision of deployment option leads the problem to be more complex as there's no guaranteed performance from the cloud or the edge. The deployment decision will be a complex issue when multiple deployment environments are involved such as IoT, edge, cloud, on-premises computation. Each of the deployment location has its own drawbacks which will influence the performance of the application when accessing to the internet, especially working with microservices deployment. The author considers it to be a gap between cloud edge deployment, and most of the existing research is focused on extending the cloud computing to edge instead of wisely replacing cloud computing to the edge. Bonomi et al. In the paper Fog Computing, a platform for Internet of Things and Analytics, introduced a conceptual intermediate for computing with the straddle of the resource from cloud to edge over network, but its discussion lacked technical implementation. Han et al. Presents a paper Mobile Fog, a programming model for large-scale application on the Internet of Things, with mapping strategy to match the hierarchy of distributed resources in cloud and edge. And the adaptation deployment was not in the scope of this research. Matogui and Rich presents a constraint-based architecture for automatic software deployment in the paper, a middleware architecture for automatic software deployment. The architecture allows user to attach the predefined constraint for the application, but it is not considered the non-functional requirements. Another paper written by Scarlett et al. Supplies an approach for optimizing resource allocation between the cloud and edge that reduce the latency and computation cost, while its approach does not allow customization of user rules. The author introduced a new framework called Data-Driven Automatic Deployment, DDAD. DDAD is an automatic application deployment framework that wisely selects the allocation in cloud edge environments. The MapK model is still the backbone of DDAD. They create some basic components that map with the function of the MapK model. For the shared knowledge, they create an app model to capture the diversity of the application and their requirements. It is not only store the state of the service, but also allowed user to define the associate dependency. The services could be resources or NFRs, which help to optimize and define the deployment environment. Parameterized base data would be stored in the app model that is required for runtime, and the data stored could be reused for other applications or services. A device manager is a lightweight service running at the edge for deployment. It is a controlling manager and to monitor the availability of resources at the edge, which is used for interacting with the cloud. Deployment planner is used to calculate the best placement plan for deployment across the surfaces with the available resources. Deployment surface is used for initializing the deployment, which could be done manually by operation staff control at the host or semi-automatically using a continuous integration server if a newer version has been committed. Monitoring components of QoS Watcher and CEP engine The QoS watcher receives monitoring information from the device manager, which will forward to CEP engine for analyzing. The CEP will decide if the alarm is necessary to be raised in accordance with the user-defined rules. For example, the CPU utilization, the response time, or the round-trip times. The data architecture components will be interact with each other, and the whole process can separate in about 10 stages. At first, the deployment surface invocation manually or automatically. Then it will send a request to the deployment planner to contact the app model. The metadata gathered by the app model and design the potential placement location and forward to deployment planner. Then the deployment planner and solved a CSP, the constraint satisfaction problem, will produce the optimized placement, which sends to deployment service for the next. The deployment service will then instruct deployment manager to download the application for operation. At the sixth stage, each service will start streaming monitoring metrics together after initialization the registers in device manager. All these metrics will be sent to QoS watcher for storage and further analyzing in the CEP engine. If any rows was broken, the CEP engines creates as a guard, acts as a guard, and raise the alert and coordinate with QoS watcher for callback services. The callback execute by QoS watcher and updates the system state. At the end of the cycle, the system will self-determine whether it should be shut down or continue the stream metrics. The author also set up the 4 prime constraints. Each service is associated with one host. Each service has been granted necessary permission and license to be deployed at the host. Ensure the resource demand of a service do not exceed the available resources. Host has the required application that the compatible with running the version of the required services. For the evaluation process will be relayed on the DDAT framework to decide whether the scoring process is in cloud or the edge. The purpose of the evaluation was to demonstrate the DDAT could integrate the cloud edge resources in a transparent manner and utilize its characteristics to ensure all user rules are on the track. The author have set up the simulated edge devices in AWS EC2 instance with each 2.4 GHz CPU core and 0.5 GB of RAM, and installed the device manager and data acquisition software. They monitor 45 machines with 45 requests to be scored every second and set up the CPU utilization in cloud and edge devices that not exceed 60% and 75% respectively. It aims to prevent the primary task from being affected by the scoring. Alert for RTT also set up for evaluating the NFRS. For evaluating the results, they compare the CPU utilization and RTT for local scoring, the cloud scoring, and with runtime adaptation. The results show that it reduced nearly 90% of CPU utilization with runtime adaptation and only 3 violations in RTT result. For evaluating the surface placement, they examine how much time is required to complete the CSP and the surface plans generation. The experiment used 60 hosts and gradually increased the number of the deployment. With the final result, there were 215 surfaces deployed, in which around 25% deployed in cloud and 25% deployed in edge, with the rest 50% can be deployed in both environments. Although the figures are not optimized, the result is satisfactory. For the critics, the author presents a state-of-the-art framework that might broadly be used in the future, since the number of IoT is increasing nowadays. However, the simulation used AWS EC2 as edge devices, which is far different from the real IoT environment, as IoT or edge might be used in different situations, such as outdoor or poor network connection. The AWS EC2 provides a stable network environment. The author might consider including physical IoT devices such as Raspberry Pi, which deployed in an adverse environment. For example, the poor network in the testing set, which will be closer to the real production environment. This is my presentation for paper 3. Thank you.